All right, today we're jumping into a paper that honestly proposes a pretty wild new way of looking at one of the most exciting technologies out there, superconductors. What if the key to understanding these, well, perfect conductors isn't found in smooth, clean math, but in the jagged, messy patterns we see all over nature?
And that really is this central question, isn't it? It feels like a total paradox. On one side, you've got the chaotic, infinitely complex world of fractals, and on the other, you have the perfectly ordered, zero-resistance flow of superconductivity. But as a couple of researchers, Elna Bulzi and Anna Kuhl, are suggesting, these two worlds might be way more connected than we ever thought. So, to see how these two seemingly opposite ideas connect, we first have to get a handle on the specific puzzle that physicists have been wrestling with when it comes to superconductors.
I mean, superconductors are just incredible. Just think about it for a second. Power lines that don't lose any energy as heat, or MRI machines that are way more powerful and efficient than anything we have today. That's the dream. And this magic all happens when you cool the material down below a certain temperature, and poof, its electrical resistance just vanishes completely.
Okay, so here's the catch. While we've got a pretty good grip on the simple classic superconductors, the ones that are really exciting, the high-temperature ones that don't need ridiculously expensive cooling, they're a mess. Structurally, they're super complex, full of holes, almost like a sponge. And our standard, clean mathematical models, they just completely fall apart when they try to describe them. So if your old toolbox doesn't work, you need new tools. And this brings us to the first part of the big idea here. What if we stop fighting the messiness and start embracing it with the mathematics of fractals? You've definitely seen fractals before, even if you didn't know the name. Think about a coastline. From space, it's jagged and complex. Zoom in on just one bay, and it's still jagged. Zoom all the way in on a single rock on the shore, and its edge is still jagged. That's a fractal. It's a pattern that just keeps repeating itself, no matter how close you look. It's everywhere in nature. Snowflakes, lightning, you name it. And this is exactly where the paper drops its first bombshell. The researchers are saying point blank that these powerful, high-temperature superconductors aren't just messy by accident. No, they have these internal fractal structures. And it's precisely this complex, jagged geometry that might be the secret to how they work. So if the material itself is a fractal, then maybe the way we measure things in that material needs to be fractal too. And this is where their research gets really innovative. This is really the heart of the whole paper. They've come up with a concept they call the fractal temperature derivative. Now, don't let the name scare you. It's basically a new kind of calculus. Instead of measuring change along a nice, smooth curve, it's built to measure change along a jagged, broken line, a line that actually behaves like the porous, complex structure of the superconductor itself. Probably the best way to think about it is this. Standard physics is like measuring distance on a perfectly straight paved road. It's easy, it's predictable. This new fractal approach, though, is like trying to measure a coastline. The closer you look, the more twists and turns you find, so the old rules just don't apply. It's a tool that's built for a messier kind of reality. And here's the really cool part. They built a control for this new tool. It's a little variable they call alpha. You can just think of it as a fractal dial. When you set the dial to 1, the math behaves like it always has. That's our smooth paved road. But as you start to turn that dial down toward 0, the model becomes more and more fractal, which lets it better describe those jagged, complex systems we've been talking about. So, the big question is, does it actually work? Well, let's take a look at what happened when they used this new fractal model on the physics of superconductors. We're going to look at the actual graphs from their paper. Okay, let's break this down. This first graph shows a really key property, how strong a magnetic field you need to basically shut down the superconductivity at a given temperature. Now, see that pink line where alpha equals 1? That's the standard prediction from the old model. But look at all the other curves for different values of alpha. They follow completely different paths. For materials that don't fit the old rules, one of these new fractal curves could be a perfect match. And this is brilliant. It shows the model's power for another property called heat capacity. When a material turns into a superconductor, there's a sudden jump in how it absorbs heat. The standard model, alpha equals 1 again, predicts that sharp, plunging drop you see. But by just tuning that fractal dial, their new model can predict a whole range of different jumps, which is exactly what we see in real-world messy materials. Now this is even more impressive. Under certain conditions, their model can actually predict a positive jump in heat capacity.
That's something that conventional theory really struggles with, but it's a phenomenon that has actually been observed in some of these really exotic superconductors. This shows the framework isn't just a minor tweak, it's describing entirely new physical possibilities. All right, so what does this all mean for the future? Let's get to the bottom line, the real-world impact of thinking this way. So here's the key takeaway. That fractal dial isn't just some math trick. It actually lets physicists create a whole spectrum of models. If you've got a simple, classic superconductor, you set alpha to 1. But if you're working with those complex, messy, high-temperature materials, the holy grail of the field, you can just dial it down to create a specific model that actually fits. And at the end of the day, this matters because a better model gives us a much deeper understanding. If we can accurately describe the physics of these complex materials, we can finally start to engineer them on purpose. This could be the key to designing brand new superconductors that work at higher and higher temperatures, and that paves the way for everything: lossless power grids, super efficient motors, next-gen MRI magnets, even quantum computers. And that just leaves us with a final, pretty mind-bending thought. This research took a fractal lens and applied it to temperature. But what happens if we start applying that same lens to other things? To time, to gravity, to space itself? This work doesn't just give us a new tool for one tiny field. It suggests a whole new way of looking at the complex, jagged, and honestly beautiful universe we all live in.